Okay, why don't we get started? Today's presentation is on VoltVar control, and I'm going to turn it over to Dr. Shrivastava. Um, and did you guys work it out? Your name's first, so WSU going to go first?
Yes, yeah, I'll go first.
Okay, all
Yeah,
right.
even
Turn it
though
over to Dr.
we are
Shrivastava.
presenting each other's slides, but okay. So today we are going to talk about this voltage control architecture, and we know that there's a lot of work in literature, and of course this is something that we use in field for voltage control and changes going on with DER integration. So let me, actually, let me first acknowledge all the contributor, which is a student at WSU Nilay Patari, Rabab, who is a student at MIT, and postdoc Subir Majumdar at WSU, and Venkatesh Venkataramanan, who is a postdoc at MIT, and also was a student here at WSU. So again, we are team tagging to talk about these two, and we are going to divide into kind of two part. One is introduction and one of the distributed algorithm, and then through another distributed optimization algorithm pack, which Professor Annasamy will talk about. All right, so first, a very quick introduction that VoltVar control is known in different names. You can say VVC, VoltVar control, VoltVar optimization, VVO, or CVR, conservation voltage reduction, and power factor control also sometimes is used. And these are just example. We have seen variation in the, but typically it points to where we manage the voltage and we manage the reactive power and maybe sometime energy saving in CVR to do the voltage control. There are multiple standards around this. In USA, we typically follow this ANSI C84.1, which is means to regulate the voltage within plus minus 5%. While in Europe, we have more common EN 50160, which allows till 10% deviation. And typically, we achieve this objective through capacitor bank, through transformer, where we can change the tap. And then, in old days, we also used voltage regulator with some switching of even inductors, but typically that's not used much now. And in future, we are looking for, and even there are some demonstration project already there to coordinate with DER or distributed energy resources with includes, of course, battery, any other DG, which can be controlled with faster timeline and more flexibility. So if you look at the VoltVar control, there are several different way of doing this, and we can broadly classify that as a local, decentralized, distributed, centralized, holonic, hybrid, and we'll talk about each of these. So in local control, as the name says, everything is, which means that sensing and actuation or control mechanism, both are local, though no signal is flowing out of the control device and what the digital control is located at that location. So in this case, if we have a cap bank or we have a, in PV system, we are using its own sensing or energy storage, all will have its own control and there will be no communication among the controller mechanism. Okay. So local is no communication, and also the control mechanism could be anything that we can develop and put using the local sensing, which could be Droop or any other things. Next, and local was the one that was done, in the beginning, which means that distribution network, when it was designed, local was the first one to start with. And then slowly we realized that if we can coordinate between the two different control devices, we can achieve a better result. And then came the decentralized. Now decentralized will also be, will include something where you use substation devices and controller and coordinate with other controlling devices for voltage control. Again, those are the same devices which is talked about. or even between two devices will be a decentralized. So decentralized is something that in a cluster, we can coordinate the control device operation with the same objective of voltage control and reactive power control. Okay, so here you see a couple of clusters which is shown by N, N6 and N2 and N3. And then came the Smart Grid Demonstration Grant, and we realized that we can make it better and we can be aware in distribution system, management system and control center by keeping everything centralized. So the control mechanism does not need to be very centralized, but even in terms of coordinating everything on that feeder and being aware and updating in the ADMS, right? So this requires a lot of more communication, computation kind of implementation, but the essence is that here all the control devices need to be controlled in a coordinated way with the central control schemes. So even the load tap changer, if there are multiple, all of those, and of course, and switch cap bank and energy storage. Now, when we try to do that, the first was without DR, because again, DR is mainly in pilot phase, while we typically do the cap bank and tap changer kind of operation. And then come variation in that, and with building on top of decentralized, centralized, and local, we can develop a hierarchical where we coordinate between like a tree structure where the root is on the supervisory control that on the top, and then it is divided into the cluster and cluster coordinate among themselves, and then talk to the supervisor to basically keep the voltage within the limit. So hierarchical structure, I would say it's a combination of decentralized and centralized, but in a tree structure. And the one which we think is going to be coming more and more in future, especially with increasing number of control devices, is going to be distributed. Now, there are some pilot phase, but it's limited much more in theory right now. And that's why more work need to be done, that how do we implement. But in distributed, these controllers will exchange information only with neighbor. There will be no supervised, there will be no leader controller. And by exchanging information among each other, they will still reach the centralized optimization or close to that, if not the fully optimal solution. So again, in doing so, we want no communication with any lead controller. And there are a lot of advantages of this. The first, we are getting optimal solution. Second, it is very robust to failure, because if one part or one controller is out of service, it still will work because others will coordinate and do its own optimization. And that's why we're going to spend more time today on distributed, because others have been in field for a long time. So to summarize, old VAR control architecture, local is something where everything is purely local, which means that there's no communication between controller, and sensing is done and actuating is done locally using some kind of control mechanism. Decentralized, where we divide the system into clusters, and each clusters have one lead which will coordinate the control devices among that cluster. In centralized, we want all the sensor and actuator to coordinate with the lead controller and or need lead software control mechanism or supervisory to reach the optimal result. As you can see, among all of these, centralized will always give you a most optimal result, even though it may not be very robust. Distributed, we have each controller talking to each other, and with the goal of reaching the similar optimization result and as optimal as possible, like a centralized, but at the same time, the communication is only with the neighbor. It's more robust, more scalable, but more work need to be done before we implement in the field. Hierarchical hybrid holonic is a combination of these, Hierarchical will be combination of decentralized with the supervisory controller. Hybrid will be any of these local. So some of the power control devices or voltage control devices are doing following local and other are decentralized, and that would be hybrid. And then finally, holonic is another new term. All holonic control means that which is simultaneously whole and apart, which what we mean by that is that we implement a control algorithm which can adopt as the operating conditions are changing. So if I'm an island, let's switch to distributed. If everything is connected and I need to tell the DMS that what I'm doing, then keep it centralized because that's the most optimal. And most probably it's already implemented. So how to design holonic control architecture will depend upon what we already have and what we can take next step, right? Again, another representation of local, no communication among each other, decentralized, where there are clusters and all the sensor or compute, which is also a computing node, and the controller are talking to each other, right? And can also talk to the control devices could be any from tap changer to cap bank and DERs. Centralized, all devices has to report and being coordinated, and they will get a signal back that or set point back to be controlled. In distributed, we only talk with neighbor, and even if some are not controlling node, you keep exchanging information till you reach to the another controlling node, and then you implement that. And if hybrid is combination of some, holonic is also being able to adopt between those. And the last one is hierarchical, where this is the top layer of control, which will coordinate among those two and having some set point. So there's a lot of details in how do we implement, and you can collect a bunch of resources to study and talk about these. But here are some in terms of local approaches, and typically those are designed in group-based method, and especially we can embed that in Poltronics controller, this kind of group which will respond to in just the local sensing measurement. We can have optimization-based hybrid approaches, even in local in some way to embed, which is of course not will be as optimal as centralized. Then centralized, we can also implement optimal control using conventional mathematical approaches or heuristic approaches. Decentralized approaches can be, if you look in the literature, are typically again talk about mathematical optimization because there's one supervised controller within the cluster which is trying to do the same thing what centralized does for the area. And then heuristic approaches and distributed I'll talk about more, but typically consensus-based dynamic method or duality-based iterative approaches. So first one is, let's talk about local. In local, here is one example where we have several different capacitor bank, and capacitor is set to operate if power factor changes. So if it goes below 0.95 lagging, and we can do that by sensing the real power and reactive power, we can compute it locally. And once we have that, then we can find out the power factor, and we can put a very simple logic when to switch it in, when to switch it out. Of course, the objective is to not do a frequent switching and also keep the voltage within the limit, right? So this is very simple one example. Another one is something one of our utility partner had, and this is based on rule-based local volt var control, where you look at total reactive power in the system, and you find out when it's leading, when it's lagging, and based on certain threshold, here we call it 60-40 rule. So 60% reactive power is lagging, or 40% is when it's less than 60%, then you turn it on. And when it's more than 60% leading, then again you turn it off. So the rule is that telemeter is greater than 0 and telemeter is greater than 60% cap, then turn it on. So these simple kind of rule will still work. Very simple, is more robust because there's there's no problem of convergence like in optimization you expect. And it will give you a good result in terms of voltage. And this one we also had in looking at different possible way we can implement it, 60/40 power factor, 60/40 power factor, and different feeders. And we get similar kind of results in terms of kilowatt percentage change and kVAR and kVA percentage change. Then once you add, like let's say energy storage in the system, which is the case in our city also in Pullman, and then you have a choice to either include storage control with existing control mechanism, or you can go with hybrid approach where one will be locally operated and the others will be operated in centralized or 60/40 whatever rule is already there. So this one shows one example which we developed for energy storage system where a sensitivity factor table was used as a mechanism, which is a little bit more complex than rule-based to control the voltage locally at the storage, energy storage device, while other switch bank and substation at transformer, which is again with the tap changing, was coordinated in a centralized way. So this is something that we developed and suggested, and I would call it local storage and hybrid overall, because some part is centralized and some part are being local. But there is no coordination between those two. But using the sensitivity factor, it's inherently coordinated in some way. So here are some results for the feeder, and then we model as a PV generation, we model energy storage system. These are real regulator, real cap bank, and we showed that by this coordination, we can of course get the power factor improvement with ESS, and also voltage profile improvement. As you see, in this case, with the BSS, we can get a better voltage profile. The other thing is that average of three-phase voltage at ESS bus will of course becomes much better with its own control. And then we come to centralized, and we'll not spend much time on this because centralized optimization is something that is very well covered in literature from long time. The essence is that you are optimizing your voltage to be within the limit, and there are several different ways of formulating the problem to keep it within the band, to keep it near 1 per unit, and put the penalty. So you can move the this objective in constraint or in objective function as appropriate, and there are several variations exist. And here you are having some of the control variable, which will be like a tap operation or switching operation for cap bank. And if you include a DER, then those will be keep on including, right, with its own constraint. Decision variables are of course that we want to control the voltage, and S, which is here generation bound, and then A and S is the tap operation and switching operation for the cap bank. The constraint will, as you expect, will be an voltage on generation bound, on nodal power balance, which is, that's why we call it OPF, optimal power flow, because we need to make sure that power flow is being solved. And the tap operation can change based on this A, which will directly impact the voltage or secondary voltage at the transformer. And we can modify, or we can add this objective function to do multiple other things. So again, we are not talking much about this because this is very well covered in literature. essence is formulating the optimization algorithm in different ways possible, right? And then when we solve these optimization, the solver need to be selected in such a way that we are able to handle all this nonlinearity in this constraint. And in here, as you can see, that these three equations, when we see this quadratic term, lead to nonlinearities and non-convexity. So, and again, in solving this problem, we have to first take care of these so that we can basically keep some guarantee on convergence and ability to solve it. And these are very well known ACOPF problem. And here's the statement that even though ACOPF has been applied in the power grid for a long time, we still do not have a fast, robust solution technique. And this we have to solve only through approximation and linearization. So now this part we would like to spend most of the time is distributed volt-var control because it makes it scalable. And what we do is that we decompose the problem, and this decomposition happen in several different ways, in approximate way, indirect way, using the sparsity of the matrix. And here, as you see, that the objective function is the centralized way is the same that we just discussed here. You have to divide and decompose into each control devices, which has ability to control its own reactive power, and have the decomposition of the objective function and also the constraint which is governing that local thing. Now, even though in any way you try to do it, there will be dependency of variables and constraint with other node. And to achieve that coordination, we have to exchange some variable. But instead of exchanging all the variable through a centralized location database, we are doing through neighbor. It typically will lead to more algorithm, and then there are some tricks and different things that we can do to minimize the number of optimization, and that's why still it's work in that need to be solved in future. So we looked at in literature, and we came up with our own approach to basically have a taxonomy or how we can divide the different set of algorithm and what we should do. So first one is data exchange mechanism, and that basically emphasizes the part of that in each iteration are you exchanging the variable with field data. And if you do, and if you use that in optimization, then we'll call it dynamic optimization. If you do not, if you just decompose the problem exactly in the same way as you do in centralized optimization, then we call it static optimization. The way we implement that, do we require a central database to be to interface with all these distributed agents? We call it federated or collaborative based on that. Collaborative means that there's all the database about network and everything need to be reside on those controller and computing devices. And then the power system model, which could be branch flow or current injection, and then algorithmic type could be based on a primal variable, and we can achieve a consensus based on that, or dual method, where I think most of the, which is true optimization, I would say, because this one is more like a coordination, not a true optimization on the primal. And then this is what we're going to talk about today, a little bit more. In terms of communication, it could be synchronous, where the variable is updated in each communication bound, or asynchronous, where some are updated and the intermittent update happen. Of course, in application type, it's very similar to centralized, so you can apply it to a different one objective like in centralized way. So first one, we are going to talk about this method called OptDST with some collaboration with Harvard, and typically we can divide this distributed dual method into network sparsity based, even though network sparsity need to exist and does exist in the power grid, and that's the region that we can make this distributed work. And then classical decomposition and coordination based approach. So OptDST, if you need to select between the data exchange, there will be kind of dynamic optimization, because You use the field measurement in each iteration. Implementation type could be actually both, but collaborative will work. This one is linearized flow model. Algorithm type is network sparsity-based distribution dual approach. And then communication is asynchronous, and application type is here, especially is DR generation cost, or minimize the queue from each so that voltage is maintained. So we'll focus on these two, OP, DST, and PAC, even though there are several different methods exist. So I'll go very quickly through this so we can spend some more time on PAC. So first one is that you have to model this starting point and linearize an approximation of your full phase AC power flow. And this one is using dist flow, which is one approximation. And there are multiple paper on this if you would like to know a little bit more about. And then in single phase distribution system, we can talk about developing this formulation where active power flow and reactive power flow can be written in terms of voltage and network parameters equation, which is simple power flow equation, but with approximated. And then the voltage magnitude, as you see from here, being updated. And then finally, a current flow is being computed based on that. And then we can take this linearized flow model for single phase. And here we do ignore or assume that line losses are less. And from there, we can design a multi-phase distribution system for, especially in this case, it's 3-phase. And then we can put this voltage vector, active power injection vector, and reactive power injection vector, which need to be updated through this set of equation. So the way we make it distributed is that each controller, and this is, there's no network model in implementation. Basically, it represents a field measurement that is coming, which is VIT. And each controller will take its own measurement, which is locally available by measuring it, and then generate a set of reactive power updates from each controller by taking its own voltage measurement, and finally giving the control signal, control action, which is changing its own reactive power. And that will impact, of course, the grid operation or network model. And here, the logic, what goes inside the controller is important, and that is based on this gradient descent two-step approach. So primal update and then the dual update, right? And we can do that because we in the primal variable and within also exchanging the dual variable. So in this way, it's distributed, and then finally, in terms of more steps that is being done is first you measure the voltage, and then you calculate the update in your reactive power locally, and then your dual lambda, and then finally step 3 you find out the injecting reactive power, and then you communicate to your neighbor, right? There are advantages and disadvantages. Advantage is that it's a good trick to solve the distributed, still get the good result. Disadvantage is that it requires multiple switching in the field. So there are more detail in this paper, and but as you can see the results that by applying this distributed algorithm, our daily load profile is, if it's given on a typical day, we can show that voltage control will be much better and with less dip, and by changing the parameters and tuning it, we can make it very much optimal result. And the next part, my colleague, Professor Annaswamy will talk about this, about the PAC.
Thank you, Anurag. If it's okay, if you can advance the slide for me, that would be great.
Sure. Yes.
Okay, so Professor Srivastava has already set up the problem very well. So as you can see, what we are going to do now is to focus on the second part of the distributed approach that he mentioned, where we are going to explicitly accommodate the interaction with the neighbors at each point. And so we worry about the connectivity that stems from the centralized problem, where the power flow equations as well as the power flow constraints are going to have interdependencies because each node is connected with some neighbors, as that picture, the network graph shows. So what we have to do then is to then decompose these problems. And the whole idea is that in a distribution grid, you have millions of nodes, and therefore computationally, the centralized problem is going to be extraordinarily difficult to solve. And so the computational aspect of that centralized problem is what we're trying to simplify by simply distributing that computation across several solvers. So each of the local power flow equations as well as the local power flow constraints are going to be much smaller in dimension. And because of that, then you're able to essentially simultaneously solve these problems that are in the individual bubbles in a parallel manner. And so how you go about doing that is really what is accomplished in the distributed optimization approaches, ADMM and PAC being two examples. And specifically what I'd like to walk you through what happens in the context of this PAC, which stands for Proximal Atomic Coordination. Next slide, please. So the whole idea comes in because items are connected, things are not decentralized. What happens in node A connected with and affected by what happens in node B, etc. And so in order to really figure out how to break this coupling, we essentially increase the dimension of the underlying problem. And so if I want to go from this global network problem to the atomized local problem that you want to solve, then essentially what I worry about is Y1, for instance, is interacting with Y4 in the first row. So at the atom A, I make a copy of Y4. Similarly, Y2 is interacting with Y3 and Y4, and therefore I'm going to make a copy in atom B, actually of all three, Y2, Y3, and Y4. Similarly, in C, Y1 interacts with Y3, and so in fact, both Y3 and Y4 interact with Y1, and therefore I'm going to combine the computations at node 3 and 4, and Y1C then is a copy. So now I have additional constraints, which is that I've made up these new variables, which are Y1C, Y4A, etc. And so they have to converge to the true values. And therefore, you have additional constraints, which is represented in the form of AJA equal to 0. That's it. That's basically the idea here. So now that you have atomized it, you now have a primal step that you have to solve, which is the solution of AJ. And you have built a augmented Lagrangian, and then you solve the coordination step, which is what is step number 2. But in addition to this coordination constraint, you also have your original power flow constraints, for instance, that's the GA equal to 0, and that's the atomic dual step that you solved, which has the mu variable. So mu and nu are your dual variables, A is your primal variable. However, what you've done is you've simplified the problem in that in each atom only has to solve a much, much smaller dimension in the J coordinate, and therefore you can solve all of the J atoms in parallel, and that basically is what is the idea. There are some more technical details, which is that I have to add regularization. Next slide, please. That regularization is what is represented in the form of the second, third, and the fourth term in the Orgman primal solution, and this allows us to basically simplify the dual update, and it keeps things linear, and so that's the predictor. So when you do this, you basically are able to do two things. One, simplify the problem so that computationally you're able to converge to the true value. Second is that you're able to essentially keep your variables and your computations private. only AJ and new hat J is what you have to broadcast to your neighbors. Even then you broadcast only to your neighbors, not to the entire network. However, the ones that are more important, such as mu and nu themselves, are private. And by introducing additional time variations in the gamma step sizes, you're able to add more obfuscation and not really reveal things that are sensitive information. For instance, if this relates to a market and you're trying to do bidding, some of your dual variables would correspond to the prices that that you're able to afford, and that will depend on cost curves that are sensitive. And therefore, you can preserve this and protect them. And that's the nice thing about this PAC algorithm. And then the theorem says everything will converge and it'll be fine. You'll be able to optimize and stay feasible in that you'll satisfy the constraints. Next slide. So this is the idea. And so we apply this to the particular problem that Anurag mentioned, which is that I have a specific cost, and here I'm going to include line losses, I'm going to include generation cost, and also so essentially it's social welfare and a combination of line loss. You have all of the power flow constraints that was mentioned earlier, and the power flow equations that are, and right here it's nonlinear, which is the one that corresponds to the constraints Vj equals Vi minus etc. And then the branch flow equations, which is also nonlinear. Next, if you can click. Then that gives you a way of setting up the problem, and we have to decompose, which is what we do using the methods that I showed you in the previous slide. And so essentially you have different primal variables at each of the feeders and the nodes and the terminal nodes, which and they change depending upon whether you have flow variables or you only have nodal variable injection variables. And then the corresponding prices, which are the dual variables, to tell you if this corresponds to a market problem, that this is what you would need to bid and would be represent the marginal cost. Next slide. So we also were able to incorporate other devices, and as you saw in the examples that Professor Srivastava mentioned, you need some of your DERs might not be DGs, but storage variables. And if it's storage, then the optimization gets stretched over multiple periods because you have to worry about the entire time it takes once you've discharged the storage for it to get charged. And so the capital T that you see in here basically is added to the overall size of your decision variable, and therefore that explicitly is accommodates some of your agents being storage agents. Next slide. So by doing all of these things, then we were able to expand the scope of what we did. And here is a specific implementation of the PAC algorithm. So we applied it to an IEEE 34 node, so three-phase unbalanced. And we essentially parallelize it using the PAC by separating it into 34 different atoms. And so essentially your J in here, at every node, it does its own thing and it computes the appropriate optimal injection variables in order to make sure that a certain cost is optimized. So we looked at 3 different types of costs that are mentioned in here. One is the standard VVC problem, so regulation around some set point. And as again was mentioned in the earlier slide, exactly what these set points are differs from an application to another. But in this particular case, we chose a specific VJR, real part and imaginary part. We also tried other objective functions such as line losses and feed power. And the idea here is basically to take this whole volt-var control and expand it to the case where we have a significant amount of penetration of renewables and demand response, right? So all of the cases that we're looking at are the ones where there's a significant amount of demand response and PV. So case A is like baseline, where you have all of the devices that are more what is currently done in terms of implementation, like such as the tap changers and cap banks that Anurag mentioned. And B, C, and D are basically forward-looking. So what happens if every node has a certain capability of demand response? What if every node has a certain amount of PV? And The percentage of PV might change, but we are assuming that each node in here is smart and is capable of not only providing the DGs or having demand response or storage, but they're also capable of course, communicating with their neighbors. And so in such a case, what happens, and we took data from ISO New England and utilized, we assumed that out of that amount of fixed demand, a certain amount is actually variable. All right, so next slide. All right, so these are the results that we got. So there's a lot of information in here. So let me try and focus on the most important ones. So A is your baseline. And so you can see that there's a certain average, and then it basically goes below the desired minimum. And what you're trying to do is to basically improve the average as well as the minimum. So if you go all the way down to the bottom and look at case D, you can see that with both demand response and PV, both the minimum and the average voltages are improved. So the specific case that gives you this result is what is called here, referred to as D6050. And what these numbers basically mean, it corresponds to the percentage of nodes that had the PV capability and the DR capability. So 60 corresponds to the PV, 50 corresponds to DR. So that's the amount of penetration we assumed in the problem. And then in each one of those demand response, we assumed that 10 to 30% was what was curtailable. So by having this kind of a capability, and we have a distributed implementation of this computation exchange information with the neighbors, the PAC is able to basically achieve VVC. So that's basically the takeaway message in here. In between, all of the different cases basically tell you that there is some sort of a disadvantage or the other. If you go to case B, for instance, we can accomplish what you see in those slides, but you need to have more flexibility in the curtailable load. So you need to go up to 50 to 80% of curtailable load. And in that case, we are not assuming any kind of DG. So if you have DG, then that brings us to D, which says that there's more degrees of freedom, and therefore you can do more with that and achieve better performance. C is the flip side of it, where you don't have DR, but you only have PV. But the problem simply is that PV is not available at all hours, and therefore to boost the voltage at all times. So anyway, if you look at a combination of all of these things, it gives you an idea of how we're going to try to take this research forward, and how you can try and accomplish better VVC with a different percentage of penetration of DER. And of course, as Anurag mentioned, we are yet to actually implement this. And so the next steps, and of course, there's lots of challenges, but there are also opportunities as well as to how we can take this and implement it. I think, so this gives you basically a different kind of a visualization, the same result that I mentioned before. Ultimately, what are we looking for in a distribution grid? We're looking for a distribution grid where you have all this intelligent edge, right? That's what you keep hearing about in pretty much every power system talk or report or initiative or what have you. So this basically gives you a snapshot of what this intelligent edge can be. So what you're seeing in here is, for instance, how the resources are utilized over a 24-hour period. So it's a temporal representation. It's also a spatial representation, because the y-axis basically shows you which of those resources are turned on or turned off. So if you want to accomplish objective 3, for instance, which I believe was line losses and I forget what the exact component was that we were, performance metric was that we were looking at. But if that's your objective, what this is saying is that this is the kind of power factor, variations that you want, and all of the red corresponds to DR utilization. So when something is white, that means that particular DR is not being utilized, etc. And the DG is the second part, and the power factor setting is what is shown in the bottom. So all of this basically says that here is the kind of a fine grain utilization of these DGs. And with this kind of a utilization, and you really exploit these degrees of freedom, you can accomplish this kind of an objective. Right, so that's really the idea. So the combination of resources basically provides you different support. And again, the point is, depending on what you want to accomplish, you get different settings. So objectives you a particular type of profile that you elicit from your DERs, and objective 3 is different. So that's the point that I would like to make with this slide. So next, so the summary is basically that when you use distributed optimization, you can coordinate these devices and you have effective resource utilization. And we can take this, and I didn't talk about markets here at all, but you essentially, if every one of those resources is owned by a different agent, you obviously have to have some sort of an infrastructure for them to all come together and provide the support that we want. And that would require a market structure. And so you can, by utilizing some of the dual variable information that we have, that gives us a directive of how the market bids and settlements can be structured. And we have all of these other attractive features, such as preserving privacy of information. So I believe that's all that I would like to hand it over to you, Anurag. Thank you very much for helping me with the slides.
I need to figure out how to unmute.
Okay.
All right, so I'll go back and maybe in next 5 minutes, I'll try to conclude that. So if we compare, and we are not putting the hybrid architecture here. So first is communication requirement. Centralized will require high, I would say. So these terms here is high, very high, and low. So local will not require any communication, so it's of course low. Centralized requires high communication. Decentralized is almost same because you're still working in clusters. And distributed can require medium or very high, depending upon that how do you implement it. In terms of computational requirement, centralized has this central node which with lots of computational requirement and maybe with server and everything. And then edge device has very low because it's only sensing and actuating, not doing much computation. In decentralized, almost same thing. But cluster lead node does not need to have a very high, but just high should be okay. In local, it should have low to medium because there are some computation being done. And distributed, it should have medium because more computation need to be done when we implement these kind of technologies. Right? In terms of performance optimality, we know that centralized at least will give you optimal result, so very high. In decentralized, it is suboptimal. In local, it's not much. It's, I would say, very low because there's no optimal optimization coordination going on. And distributed should give you fairly good response, and depending upon how we design, it is robust with less communication requirement. At the same time, has the performance as a centrality or very close to that. And the last one, I would talk about resiliency, which is very important to consider as we move to the next, design or next operation of Power Grid with more and more DER. That centralized is not very resilient, and the reason is that it is a single controller depending upon communication with so many different set of devices, and if one fails, it will not be able to do it. So single point of failure makes it, even with redundancy, it is not very robust, and also the attack vector will kind of propagate in this. In decentralized comes around medium because it's a cluster, so one cluster is problem, another cluster will work. A local is, I'd say it's pretty resilient, even though it's not giving much performance. And distributed is something that finds a balance between performance and still being, much more resilient compared to others. So just to summarize that we discussed about multiple control architecture for volt-work control, with its own advantage and limitation. And we know that with increasing DR, centralized will not be scalable, and we have to look for other possible solution. Local is possibility, but that's not optimal, that's not coordinated. and hybrid or Holonic might help. These alternative control architecture will not only need to seen as a performance in terms of voltage control, but also in terms of communication, computation, resiliency, and economics requirement. And then finally, we presented about 2 different possible algorithm, OptDST and PAC, which are different kind with its own constraint and details. And then we all know that more work is needed before we put in this field, and more research need to be done in this direction. So a lot of different which we talked about and reviewed by the team. And finally, we'll be very happy to take questions. Any questions or?
Hello, Anurag. I think nobody is talking, so we can discuss.
Sure.
I have no question, but just I want to. I like those presentation very much because, to be honest, I implement volt-var optimization in ETAP. So yeah, I'm very happy to know some other new terms. And yeah, one thing I just try to understand. Professor Anusharmi, you already mentioned that for 34 bus system, something like that, you already mentioned IEEE 34 bus system. So you consider 34 node or 34 agent. Okay, let's say something agent or C1, C2 up to 34. That okay, you can tell, but okay, for communication purpose, what type of information you need from C1 and C2? Which information they will send to each other? The neighbor. Each other means just the neighbor.
Right. So right now, the information that they would need are what the grid the connectivity is that corresponds to say, for instance, the terms that related to power flow constraints in here. So the AJ corresponds to basically the network connectivity, who their neighbors are, and what the grid physics parameters are that come from the power flow equations. Rabab, can you add to this?
Yeah, that answer basically just summarizes all of it. To give more details, for the branch flow problem, the physical variables that are exchanged are the voltage at the node, and then one of the line variables, so Pij and Qij. And so it also depends on what model you are using. For some of the other work that we're doing, we're using an unbalanced model that doesn't have some of these variables, so that the specific information is different. But in general, it'll just be anything that another node might need in order to calculate its own constraints.
Okay, so in that case, 34 nodes and 34, each node has those values, I understand. But reality, 34 bus system, all the nodes may not have all the voltage changing or voltage control devices. Let's say in your 34 bus system, we have 4 nodes, for an example, just 4 nodes have voltage regulating device. Let's say switch capacitor and voltage regulator. Let's say consider 4 nodes only. In that case, can we get all those data? How do you get this data? But I have considered only 4, not 34.
If you
can you get all those data?
Sure. If you go to slide 29.
Let's say physical parameter. How do you get physical parameter in that case?
So then what we would have to do is to derive the correspond. So let's say that I'm assuming the specific example you're talking about, Ahmed, is we still have 34 nodes, but we only, some of them have smart aspects associated with it. Then you would have to basically work with the reduced order model with those 4 nodes, and you would basically have an equivalent line parameters, and it's those line parameters that you would have to share among those nodes, and the pack can be essentially collapsed into, the atomized with respect to those 4 nodes, and then you would have the communication between them, and all of the distributed optimization would be projected to those 4 nodes, and that would be appropriately derived.
And if something change in between, let's say load and other things might be changed or configuration is changed, then just my question is, it should do automatically, right? Otherwise,
Yes.
my
Yes.
operator, or maybe operator should have communication that operator will change something. Otherwise, yeah, if something is changed, configuration is changed, something other change, then I don't know. We then how do we run it? Automatically
Yeah,
it will
right.
change.
Then
Yeah.
we're saying for every one of those new configurations,
Yes. How do they? Yeah.
you have to then recompute is
Yeah, and
the
then-
assumption that is being made. Yeah. But those are, it's a very good question. These are all things that we have to worry about as we then, continue, expand on the research and build on it further. I think that's a very, very fair question. So how do you make sure as the configurations change as to what information is important, what information can be calculated and extrapolated?
Okay, great. And one more thing for the Anurag, you mentioned most of the time that the centralized system is not robust, and what does it mean? And can you describe actually what sense you mean? Yeah.
So robust to or resilient to the failure. So for example, if the first thing is that once we include, I would say that it's not scalable and it's not robust both, right? So robustness means that if all these control devices which are sending the data, and I know that they also send this liveliness of those controller. If it's not happening and because of so it's more complex. There are a lot of these component, communication, computing, and everything exists. If any of these fails, then it will not give you the convergence and the result. And scalable, I think, with all these more and more edge control devices, I think it's not scalable.
Actually, what I developed, that is actually centralized. That those are also always it runs actually under ADMS. But actually, logic is we work this way, that even we run any distribution study, we call per two ways. One is per feeder basis or per system basis, or group feeder. We sometimes call group feeder. But volt-var optimization mainly per feeder basis. So if I have, let's say, one substation, let's say 6 feeders, but usually a fair amount of feeder exists. Let's say sometimes 1,000 feeders. But good thing is we can run per feeder basis even. So yes, I know it's computationally intensive, but if we need, we can run even multiple system. I run 10 computers. Each computer will run, let's say, 100 feeder at a time. So in that case, yes, or even we can run each feeder. So in that case, actually, it's not because we don't need centralized system. It doesn't mean that we run all the feeders at a time. We can run even actually each feeder at a time. So in that case, actually, it's not that much intensive. Yeah,
that's true. But still, it will be the robustness will not be still guaranteed. So scalability will not be a big problem if you divide by feeder, which is we typically do. But the failure of any communication link and data server and all those kind of things will result into not working.
Will that of that feeder will be affected? Yes. Okay. All right. Thank you.
In that case, you will still have the same problem you mentioned with the changing configurations, right? So then you have to run so many with every new configuration, a whole new optimization problem.
Well, actually, when we run, always we run for the whole system. So if actually ADMS or those things real time. So if something change configuration, system will know it's changed and then it will run it. So configuration change always just because we have in real time system, we have all the connectivity all the time. Only configuration change, it means one switch is on and another is off, nothing else, right? So it does not affect much for the because we have all the because we don't use mainly not the what is called, let's say, reduced model or something. So we don't need to calculate again. Only switch on and off. Usually, if switch on and off, the system is same. There is nothing is out of service. Usually, if it is loop system or something. But well, that is easier for the centralized system, but not for maybe distributed system. Because distribution system has that power to calculate all these things because the system may not available. They don't have the model or something like that. Maybe full model they don't have. Yeah.
Thank you. Well, I don't see any other questions coming, but please reach out to us if you have more questions.
Perfect.
Thanks everyone for joining. Again.
Thank you.
Thank you, everyone.